stuck. Okay. So, John, yeah, you're already sharing, great. And yeah, whenever you're ready, you can start.
Okay, very good. So today's the last day of the little mini series, and we tie it all together. We've set up how to treat general relativity as a quantum field theory, and it fits very naturally into this paradigm, which is effective field theories, and this tells us how we can make good predictions. So the basic idea is that we know the low energy degrees of freedom. And their interactions. We clearly don't know the high energy, whatever the completion of general relativity is. This tells us that we need to not focus on the effects of the UV, but focus on the effects of the infrared. And effective field theory has told us how to do that. So there's a practical way to do that. That the UV physics, the unknown stuff, by the uncertainty principle, is local. So it looks like some term in a local action, a local Lagrangian. The IR physics, things can propagate long distances because they're massless fields. They are excited by the interactions. This can be non-local. And we've seen the calculational features of this. Calculationally, if you have powers, let's take as an example, q squared minus m squared, and Taylor expand that, m being very big and q being the momentum that you're after. This looks like minus 1 over m squared plus q squared over m to the fourth plus dot dot dot, which turns into a delta function plus box on the delta function. If I transition to a position-space description, box over m squared, m to the fourth, etc. So you get local things from analytic functions, whereas logs and other things, that's non-analytic and can't be expressed in terms of local stuff. So we've seen this in other contexts, and the goal today is to do this carefully for general relativity. So let's start. Let's just reframe the program. The idea here is that we know the symmetries, which is general covariance, and we know the dynamical variable, which is the metric. And so we're interested in writing out the most general Lagrangian that you can. And we'll use an energy expansion or derivative expansion, or curvature expansion. In doing so, we had previously been focused on the Einstein term, but in general, the action would be integral d4x squared minus g. There's a cosmological constant. There's the Einstein term. There could be terms r squared c2 r mu nu, and you could have higher curvatures. Since r goes like derivative squared, r squareds are like derivatives to the fourth. Derivatives, when you make matrix elements, are like energies, and so this is the energy derivative or curvature expansion. Okay. The one thing I have used here is that in 4 dimensions, there's only 2 terms that you need to have here. There's the Gauss-Bonnet term. It's formed with the Riemann tensor, and this guy is a total derivative in 4 dimensions. So the Euler characteristic is the integral d4x square root of minus g times this guy. And so we then don't need an extra term in the, you could have had 3 terms here in the curvature squared, so you don't need or equivalently, you could put it in, or you could put the Weil tensor in. That's fine. Now, effective field theory as a technique doesn't tell us anything about the coefficients, so you just go and you measure them. So what we did before, remember, was we matched the coefficients to the full theory. The more general phrasing is you match or you measure. In this case, we don't have the full theory under our control. So we have to measure them. Fairly, lambda is about 10 to the minus 3 electron volts to the 4th power. That's a bit of a puzzle by its size, but nevertheless, we just measure it. Kappa squared is 32 pi g. G Newton is measured, and there are bounds on C1 and C2. Okay, they are higher curvature. We live in a low curvature world. We don't see this very much, these terms very much. But if those coefficients were enormous, we could in principle see them. And here's one way that you can see them. They are of order 4 derivatives. So the you can make this more precise, but roughly, basically, if we're after the gravitational potential, we get del squared plus kappa squared C1 del to the 4th. Phi is kappa squared rho, where this is some mass density. So if you're getting a gravitational potential, you normally just solve del squared. Phi is rho. Here you get del to the 4th. So some gravitational potential. And so if those coefficients were particularly large, you would be able to see them at macroscopic distances. The way you would see this is that the Green's function would be 1 over q squared minus kappa squared c1 q to the fourth, which if you partial fraction it is 1 over q squared minus 1 over q squared minus 1 over kappa squared c. So if you just combine those up, you get the quartic propagator out there. And so this then looks like a mass. The solution then is that V of R is roughly G M over R. 1 from the first term, that's the usual piece, and then minus e to the minus mr, a Yukawa term from the second piece. If that were big enough, you would see it. And this logic then tells us that C1 and C2 are less than about 10 to the plus 65. Okay, so they're not very well bounded at all. Basically, we're insensitive to them, but nevertheless, they're in principle could be there. Okay, one of the objections that one often hears to what I've just told you is we normally don't like higher derivatives in a theory. So let me just say that and explain why it's not important here. So the phrasing goes under the name Ostragradsky. Ostragradsky was a Russian mathematician from around 1850, who looked at higher derivative theories, trying to get out Hamilton's equations out of higher derivative theories. And when you do this, you have extra degrees of freedom, just like we see there. And he chose those to get Hamilton's equations to work. So if we're doing a field theory with this, you would have 2 coordinates. One would be phi, like the usual coordinates. He chose the second one to be phi dot, and a canonical momentum associated with that was, turns out, for a scalar field theory, the m squared were and pi 2, I don't know. You don't need to really know this, but it's minus box over m squared phi. So this is actually the same cases that I have written up there with this, where that propagator gets factored with a factor of m. And the Hamiltonian then has a term pi 1 phi 2 plus other stuff. And this guy is not positive definite. So there's an instability. So the claim is an instability. So this is the calculational origin of the argument against higher derivatives in a field theory. Higher time derivatives is really what it amounts to. And these theories, when you have R squared Z, you have higher time derivatives. However, we've already seen that this is not a problem for effective field theory. It's a problem if you are probing the theory at high energies. But remember QED, we already saw this. happen. And we know experimentally there's no instability in QED, but QED at low energies has the usual piece, and then there's a F box F over M squared term. This guy is the small correction, so it doesn't cause any instability at low energies. And so there's no instability experimentally when treated as perturbation. If you got to a point where the energies were proportional to M squared, then potentially it could be, but your effective field theory changes to a different theory at those scales. And so you have a well-behaved high energy theory and a well-behaved low energy theory, and no Ostragradsky instability. Any questions about that setup?
Yeah, there's a question in the chat asking
Yes.
again, the definition of pi and phi2. Probably, I guess you can argue a little bit on that. When you introduce the phi1 and phi2 in the.
Oh yeah, I'm sorry. So this perhaps I didn't need to go through all that detail, but I just wanted to show you what the rough idea is. So this was for a Lagrangian that had phi box phi plus phi box squared over M squared phi plus some v of phi. So you have time derivatives, 2 time derivatives and 4 time derivatives. And this is the particular choice that happens if you follow Ostragradsky's construction. He takes one of the coordinates to be phi, the others to be phi dot, and I've written them out. It's not obvious ahead of time, but these are choices that then, when you form a Hamiltonian in the usual way, Hamilton's equation is equivalent to the equations of motion. Okay, so that was the Ostragradsky construction. And it's taken in modern terms to argue against theories with higher time derivatives. It's a longer story that I can't get into here, but I've given you the essential point here is that it's any instability that comes by the phrasing of Ostragradsky is not a problem in effective field theories when treated in the domain where the effective field theory is valid. Okay, I hope, does that answer the question enough?
Yeah, I mean, I think I don't know the Azal is okay with it. Yeah, okay, it's okay.
Can I ask you another thing? So
Sure.
The Gauss degrees of freedom becomes relevant instead if you outside the validity of the effective field theory
Right.
limit, right? So there are
Right.
ghosts in the effective field theory, but are outside of the validity
So
of.
there's no propagating ghosts because we don't treat the theory at energies where you could excite the ghosts.
Okay, because we are at low energies where.
Because we're low energy, so you can't excite the ghosts because they only live at high energies. And just for everybody else, the comment that the phrasing of this of calling them ghosts comes from that minus sign there. There's the propagators come with the wrong minus signs for these high mass states.
Okay.
Okay. So in the effective field theory, you just live with the low energy degrees of freedom, and they have the usual kinetic energies, and we don't have you quantize using the low energy. states only. Okay. Let's start down here. The next topic I need to do is renormalization. In a way, this is for the effect field theory is the most boring part of the theory, because we know that EFT is wrong in the UV. And so any UV physics is done incorrectly, whether it's the divergences or whether it's finite stuff, it doesn't matter. It's all incorrect at high energies. But we get saved by the fact that the UV physics is local. So it can be written as a local term. And if you go out and you measure those coefficients, you'll get whatever the correct physics is. You'll get you'll find out what the physics is, even though the effective field theory has been wrong. All you have to do is you have to renormalize the theory. So you have to renormalize an unrenormalizable theory. Okay, but that's actually easy. It of course wasn't always appreciated that this was easy, but this is one of the insights of effective field theory. You write out the general local L Lagrangian consistent with symmetries. Divergences are local if they preserve the symmetries. They can be renormalized into parameters in the local Lagrangians. Okay. So the interesting feature of trying to do the renormalization is you want to preserve the symmetry so that you can do this, and so there's no leftover infinities floating around that you don't know don't know how to deal with. You go out, parameterize it, you in principle measure it, and you've renormalized the theory. We also would like to be guaranteed that all reactions get renormalized the same way. In a way, that's part of the same game as preserving the symmetry, because there's only a small number of terms that you can put in your local Lagrangian. They're constrained by the symmetry. And so anyhow, the answer to both those issues is the background field method. Which was applied for the renormalization of gravity by Tufte and Veltman. In one of the more important papers in the literature, true classic. Basically, remember, background field method expands G mu nu as a background field plus a quantum fluctuation, which is H mu nu. And I covered this in lesson 3. And so I'm just going to pull out one of the formulas from there. This was this was the expansion of the Einstein action in terms of the background field. And the crucial part that I'm after here is that it's gauge invariant with respect to the background field. Or generally coordinate invariant if you prefer. And this will tell us that our results will be generally coordinate invariant. So in fact, the symmetry is in fact preserved. So that's good. If I start trying to look at this, it turns out it's also very much similar to the mass, the scalar field that I did for you in lesson 4. Whereas, because if I look at some of these terms here, let's pick this term right where I'm circling right now. That term, if I want to look at the effect of that, there is a tadpole type piece where this here is background field and there's a tadpole, but that goes like d4 integral ddk 1 over k squared, which in dimensional regularization is set equal to 0. So that there is no renormalization of that. There is, however, if you then used it at second order, you could have an R bar, a bubble diagram, R bar. So second order would be of order R squared. Well, involve the integral ddk 1 over k squared 1 over k squared minus q, k minus q squared, which ends up then producing R 1 over epsilon minus log box R terms, where box is the equivalent of log q squared. And so you expect divergences 1 over epsilon R squared. So we're going to get divergence of order R squared. Okay, so that's basically the analysis. By dimensional analysis is the same as the scalar field. And now's where I wish I had had a little more time to do more on the heat kernel. But the best way to do this is heat kernel. I do not have time to do this. But Tufts and Veltman did. They calculated these heat kernel coefficients for the graviton and the ghost fields. They get 1 over 16 pi squared. The divergence is 1 over epsilon times 1 over 120 R squared minus plus 7 over 20 R mu nu. You know, it doesn't make that much difference what the coefficients are, but these things then just produce a shift in C1 and C2, and you absorb them into the so-called measured values. Okay, so we normalized.
Sorry, there are not any non-local pieces in this case?
Yeah, so there are non-local pieces left over. R log box R. So the non-local piece is sitting right there. We're going to treat that separately. I'm just doing renormalization, but that is a component of something that I'll show you a piece of that in the vacuum, in the gravitational potential. Writing in this form here with the log box is a technique that Barvinsky and Velkovsky pioneered. And so there's a whole literature associated with those log box pieces.
Also, about those papers, I saw that those papers are from the 80s. Do you have any more modern references to look at those things? Because I found those papers quite difficult to read in general.
Yes, they're difficult to read, yes. There's, as always, I have a paper of my own to recommend. I have a paper with Bassem El Manoufi where we explore some of these things. We have 3 papers that have effects about log box in them. So my student Bassem El Manoufi, less than a decade ago.
Okay.
Yeah.
Thank you.
If you like my style of describing things, you'll probably be a little easier to read than their papers.
Okay, thanks.
Okay. Some comments about this result. So we've renormalized it. We're essentially done. But comments. This result is often said that pure gravity is one loop renormalizable, one loop finite. Okay, so that's often a comment made of this. And it doesn't look that way. There's the 1 over epsilon, and there's the divergences. But the point of this phrasing is that pure gravity satisfies an equations of motion r mu nu equals to 0. And so all the matrix elements of this divergence terms vanish if you only have gravitons around there. So pure gravity means only gravitons. So that's true. It's also not particularly useful. Matter exists, of course, in which case these effects are no longer 0. And it's also no longer, so it's not particularly useful in the long run, but I can, if I have time, show you a graviton scattering where this is a relevant comment. Yeah, there's also, could be said that the 2-loop divergence involves the Riemann tensor, so. All right, but I'm not going to go there. Okay, so let's. But this is the unreliable part of the theory. All we know is that the symmetry is preserved, and you need to then shift to the low energies. And so let's try doing that. I'm going to do the gravitational potential. My favorite real calculation is the gravitational potential. And technically, we're going to do the scattering potential. Which is gotten by taking the non-relativistic limit of a scattering amplitude, and then just to display things we Fourier transform it. Okay. So at leading order, we saw this way back in lecture 1. you just do graviton exchange. You take that propagator, you take the Feynman rules. In the non-relativistic limit, this goes to things like kappa squared m over q squared. You Fourier transform that, you get the gm m over r potential. So we get, using QFT, the graviton potential. Now, next order, we're going to go through this using effective field theory logic. Next order, there are these local terms. This C1 R, C2 R mu nu. Okay, if I write a little Feynman vertex for that, they look like, so there's a 2 graviton vertex R squared with a field, and this looks like one of the C's, C1 or C2, q to the 4th, because there's 4 derivatives, and so it goes like powers q to the 4th. So if I am then trying to make a potential out of this, I would do something like that. I insert this into the same type of diagram. This gives me a 1 over q squared c q to the 4th 1 over q squared, which is a constant, which Fourier transforms to delta 3 of x. Okay, so all the effects of these coefficients and the where the divergences were only influence delta 3 of x terms in the potential. We actually could have seen this previously. Previously we had treated this slightly differently. We had these effects of these higher order terms being e to the minus m r over r terms of Yukawa, so they're exponentially suppressed. But basically, this looks like a representation of a delta function. This is for a big M. It's a representation of a delta function. So the Yukawas that we gave before, when the mass is big, are just these delta functions. So all these coefficients that we don't know aren't going to change the potential at any finite distance. Okay, so let's continue thinking like an effective field theorist. And now we're instructed to do a full quantum field theory, so now do loops. Okay, so I would, we've started off doing this diagram. You might try doing something like this diagram. You might try doing something like, I'm going to draw just for later use that way. So this might be big M, this might be little m. There's a large number of diagrams. I don't want to forget to draw this one, which is the vacuum polarization. there's box diagrams, there's cross box diagrams, and there's others. I'm not going to draw them all. Okay, so if we're to calculate this at one loop level, we're instructed to calculate all these diagrams. What would we expect to get out? Well, we expect that this first piece goes like 1 over q squared. That's the usual piece that we get. So I'll just write it as gm m over q squared. So we're working in momentum space, and I get a 1 from that first diagram there. We're going to get out here, I'm going to expect that I'm going to find things that go like q squared, as I could, why not? So all of the rest of these things go like kappa squared because they have higher powers of the gravitational vertices. There could be kappa squared, q squared, log q squared. So kappa squared q squared is dimensionally correct. Kappa squared log q squared is also dimensionally correct. One that I haven't motivated for you too much, but what you do find is kappa squared. It's the square root of q squared times m squared, where m is one of these two masses here. Okay, so this is also a non-analytic piece. It's not, can't be Taylor expanded as like derivatives of delta functions. It appears whenever there are massive and massless particles. So there's a massive particle on one leg. So those triangle diagrams are good examples. If you Fourier transform this, you get, and you take, I'm taking the non-relativistic limit, and Fourier transforming V of R is the GM M over R piece. I get from the 1. This guy, if I take the Fourier transform of, it goes like 1 over the square root of q squared, because there's a square root upstairs and 1 over q squared downstairs. This transforms like G over R, extra power of R, and it's GM plus M is it's symmetric and in the two masses. The next one transforms like G, so GQ squared log q squared. So it's the Fourier transform of log q squared, goes like overall 1 over R cubed. So an extra, 1 over R squared here. And then the last piece, the q squared over q squared, is a constant, is a delta function. Okay. So looking at that, and again, thinking like an effective field, we know that all the coefficients, all the unknown coefficients, and all the divergences go into the analytic stuff. So they go only here. So all what's that left overhead, but has to be finite, and it has to be independent of any of those parameters. So we know before doing the calculation that you can get a reliable prediction. If you go back and put in powers of C and H bar, which I've dropped, well, let me not put in C's. Well, I can put in C's. This is C squared, and this is H bar over C cubed. Okay. So this is a quantum piece. And so it's linear in H bar. And so I've got the quantum correction to the Newtonian potential. You go off and calculate. It's a long and painful calculation, but you get an answer, which is V of R is minus G M over R. 1 plus 3 is the number there, G M plus M over R plus 41 over 10 pi G H bar over R squared. Now there I've done a finite, reliable quantum calculation for you. The answer is 41 over 10 pi, pure number. Hey, any questions about the procedures that I did there?
So there's a question in the chat saying, okay, does the non-analytical piece in the small m expression unit, okay, is the non-analytical piece in the m expression unit consistent? I guess that's the question.
The
Non-analytical piece in which depends on the small m.
The depends on the small m. I guess I'm not getting the point of the question.
Yeah,
it's a matter of perhaps. Are you talking about the square root pieces, which are sort of the more unexpected?
I think so, because that's the only term.
So I will say some things more about them. They come from diagrams like the two triangles. This one has a factor of, with the m there is the mass that's in the triangle diagram, and so that one has big M and this one has little m. And so the fact that these become m plus big M is just that there's two diagrams.
Was the only question in the chat, but if someone wants to.
Hello, I'd like to ask a question.
Yeah.
Sure.
So there must be two parts in these calculations, like there must be an imaginary part and there must be a real part. So my question is, do these imaginary parts contribute towards the observables?
Yeah. And okay, so the question is about real and imaginary parts. So there is an imaginary part in the box diagram. And that imaginary part, if I sum up the series of box diagrams and look at the imaginary parts, this goes into what's in QED is called the Coulomb phase. So it exponentiates. In this case, you'd probably call it the Newton phase. So, but it's shown to exponentiate in this classic paper by Weinberg, which I have wanted to discuss at several points here, and have sort of run out of time for discussing it. But it's a good opportunity to say it here, that the phases here exponentiate. You then, when you take matrix elements, they don't influence the amplitudes.
But do they not survive the, limits that we are taking in this problem? So I don't understand how these are not contributing towards the observables.
Okay, I mean the imaginary parts, because they generate just an overall phase, give you something that looks like e to the I phi times the original matrix element. And so when I square them, they drop out. I mean, there are residual infrared effects, but the imaginary parts to leading order drop out.
All right, thanks. Got it. Yeah.
Okay.
Thank you.
Yeah. Okay. I should say that this has been recalculated in a better way. This has also been recalculated using unitarity techniques. And this takes us back to that Feynman's tree theorem, which we saw was in his original paper there. And in that original paper, he proved the theorem that you can reconstruct the perturbative expansion knowing just on-shell matrix elements. And he used that to argue for the need for ghosts to remove unphysical degrees of freedom. But the way this works is that basically, if I have some blob here where I have the on-shell production of two gravitons, I can reconstruct from that the fact that these diagrams look like trees, bubbles, triangles, etc. So I can reconstruct the analytic structure of those knowing the on-shell amplitudes. And so this is these unitarity techniques are a modern way to do these Feynman diagram expansions. And then here we have the extra feature that general relativity on-shell amplitudes are like Yang-Mills amplitudes squared. The double copy of the gravity is the square of the gauge theory, which I showed you a bit in lecture 4. And in particular, I showed you exactly these diagrams here, which are the massive particles. They're the Compton amplitudes. And so you can redo the calculation using these modern techniques instead of doing the Feynman diagram expansion. You write out the Compton amplitude for photons, you square it, it becomes a general relativity amplitude, you multiply them together, you pull out the relevant kinematic factors, and you write the answer out. So it's a modern way to do that, and you get the same answer. That's actually useful because these are actually, since they're on-shell states, you don't have to worry about gauge theories or ghosts. Gauge fixing is the ghosts. They're the on-shell states. Okay. The other thing that's useful about knowing those techniques is that you can do bending of light by the same techniques. In other words, this is massless particles. You basically take photons or scalars or gravitons coming along and a massive particle, and you do the cuts and you get out the scattering amplitudes. You can convert that. So this gives you scattering amplitudes. This can be converted into a bending angle by using what's called the iconal techniques, which again I won't explain, but they're basically techniques derived from geometric optics, where at large impact parameters you can take an amplitude and turn it into a bending angle. And let's see, I have the results. Let's copy it. Okay, so the bending angle, turns out you get the leading piece from one graviton exchange, you get the first classical correction also, and you get a term that's proportional to h bar quantum correction. It's interesting that you get the correct classical expression out of the Feynman diagrams. I'll come back to that in a minute. Yeah. I'm going to, I had prepared to do graviton scattering. But I think I'll skip that for lack of time, just because it doesn't add too much to the discussion. It's another nice example of a finite calculation where you can make sense of things, quantum physics for general relativity. But other than that, it's just another good example of the effective field theory paradigm. What I do want to do, though, is I want to go back and talk about some of these things and pick out some lessons. So actually, since I've done the calculations there, I've showed you how to do the calculations using the pulling out non-analytic stuff. Maybe I should take questions before moving on.
Okay, there are no questions in the chat. So
Okay.
But
Okay.
okay.
can I ask
If
one?
anyone wants to ask them, though.
No,
it's
but
good
there's a
to know.
question. There's a question.
Yeah, can I ask one about the quantum correction to Newtonian potential?
Yes, please.
So the classical piece in there is like a GR correction.
That's correct.
And then my next question is, would you be able, like, with these techniques to find metric functions? So not in the not considering the non-relativistic limit, considering fully relativistic
Yes.
quantum corrections to metrics. Is it doable?
Yeah. So, okay, so that is part of my lessons. Lessons comments. So why don't we just postpone that and see if I answer it
Sure.
automatically in what I'm about to say. Okay. So from the various things that we've done, we can pull out some lessons that are, I like to call them low energy theorems of quantum gravity, because they're things that have to be true no matter what the high energy theory of gravity is, as long as it reproduces general relativity at low energies. Okay, one of them is that that potential is universal. The parts of it that I showed you that was first found by Ross and Holstein by doing the calculation for different spins, for photon, I mean, not for photon, but massive particles, but spin 1, spin a half, spin 0 in all possible combinations. And the diagrams are different. Each of the steps is different. The answer always sums up to the same thing. And this can be understood by the unitarity techniques. When I showed you the Compton amplitudes for photons and gravitons, I commented that there are low energy theorems that tell us that those amplitudes, the Compton amplitudes, are universal. And so basically, if the individual amplitudes are universal, you can trace that through and find that the one loop amplitude is also universal. So that 41 over 10 pi is independent of whether it's an electron or a Higgs boson or the moon. It doesn't matter. It's the same number for anybody because it's obtained just by knowing the Compton amplitudes, which are themselves universal. The second feature I wanted to highlight here is that we've got classical effects from loops. Okay. Now, normally, one is told that the loop expansion is an H-bar expansion. But that's actually not true. It's often an H-bar expansion. You do get H-bar effects at one loop. We did, but you also get classical effects. And the reason that this folk theorem is not a real theorem is that you, in proving the folk theorem, you're hiding some hidden factors of H bar. So here's how it works in practice. Let's imagine I'm doing a fermion. The Dirac equation with the H bar in there has an H bar in front of the derivative. And people will pull out a factor H bar from the Lagrangian. And then when you use the Lagrangian in loops again, you're counting these powers of H bar. And that's how you end up proving the folk theorem. But there's a hidden factor, this M over H bar, which can sometimes compensate for it. And we saw that actually happening. The Q squared, M squared terms were the ones that gave us the classical effect. So if they really had an H bar out in front of it and put an H bar squared there, this was then classical. Okay, so you can get classical effects from loops. We've seen it in two cases here. One is in the gravitational potential. There's the post-Newtonian correction, and then there's a post-Newtonian correction in the bending angle, which we get correctly also. So this has become a little subfield. In gravitational wave physics, the quantum field theory techniques have been used to pull out gravity waves. And so somewhat surprisingly are competitive with the classical gravity calculations. The quantum field theory techniques have been boosted by this feature that the gravitational amplitudes are squares of gauge theory amplitudes, and unitarity techniques have been used. And so some of the great field theory developments of the past decade have gone into this. But it's important to know that there are classical effects from loops. Okay, so it's a little subfield. The third thing at this stage, I will, after this next one, I'll stop and ask if I've answered the question already. There is no test mass limit for quantum effects. Okay, and this is actually an interesting one. That's relevant. We're going to go back up here and notice that the quantum effects are independent of the masses. The classical piece, if I took one mass very big and one very small, I could neglect the very small mass. So in those terms, I could neglect the masses. But in the classical piece, setting the mass equal to 0 doesn't do anything. And you can actually see that in explicit diagrams. If I do the diagrams that give me the classical pieces, this is big M, this is little m, big M, little m. Classically, this goes like m and this goes like little m. So I could neglect little m for the classical pieces. Quantum mechanically, so this goes like square root of q squared, m square root of q squared. This goes like q squared log. This goes like q squared log. They're identical. You can't neglect the quantum corrections. And it's not too surprising because no matter how small this is, the graviton can propagate long distances, and you actually are feeling the potential at a different place. So you can't say that the light mass doesn't produce a disturbance in the field. So the question before about the classical effects, have I addressed those sufficiently to satisfy the questioner?
Are you referring to my question about the relativity?
Yes, no problem. Yes.
I kind of didn't understand. Can you please elaborate a bit more on that? Because I was asking about the relativistic limit, like if you could get a correction that goes into metric functions instead of Newtonian potential.
Okay, I'm sorry. So if we're for the relativistic limit, the bending of light actually is a relativistic calculation because the massless fields are always relativistic. But the second part of your, so I've not used the non-relativistic limit there. The second part of your question is whether it goes into a change in the metric is the point I'm going to address next. So now let me wait one more time and we'll see if
Okay.
this is it. Okay. So one of the features that I immediately was interested in was, for example, can I do quantum corrections to the Schwarzschild metric? And I wrote a paper where I calculated them. That paper, unfortunately, is incorrect, and I'll want to tell you why. So this little part I'm heading is that there's no quantum metric. So making quantum corrections to the metric is not exactly a valid quantum question. So for example, there's no well-defined quantum corrections to Schwarzschild. Even though if we just go off and try calculating, we get an answer. And it's in a way, maybe it's not surprising, though it did surprise me. Because we don't talk about the quantum corrections to the electric field around an electron. We do scattering amplitudes with electrons. We don't, it's not a quantum electric field, if you want, quantum corrected electric field. And the basic point was picked up by Kierlin. And Kierlin showed by calculating that it's not invariant under field redefinitions. In other words, this thing that we call Hogg's theorem does not apply. Hogg's theorem only applies on shell, and this is off shell. So this is basically the calculations you're doing are like off shell partial amplitudes. So if you do it using one set of field variables, Kierlin will come along and using another and get a different answer. So there's no well-defined answer. And it's basically that this is not a good quantum question. But then that sort of leaves open an interesting research problem, which is still not completely solved, is what is the right, well, there is obviously some interest in what does quantum mechanics do to Schwarzschild. What is the right way to calculate that? And using appropriate quantum calculations, which are presumably scattering amplitudes of some form. And it's just technically challenging and not answered yet. There's some way to address the corrections, but there's not going to be given by just giving a change in the metric. Okay. So maybe that's now hopefully gets closer to Marco's question.
Yeah, yes, it does. Thanks.
Okay, good. Thank you. Something I didn't point out when I was doing the bending angles is that the bending angle, so there's some formula. It's I only pointed out the H bar. It maybe I should have pointed out the dependence. B is the impact parameter. How close to the object you get. But there is actually a non-universal feature here where scalars, photons, gravitons, and also now we have fermions give different numbers. They even go in different directions. So there's not a universal. So I'm going to put that down here as a separate lesson, is that massless particle effects are not universal. And there's no reason why they should be, in the sense that the diagrams are different and there is no universality of the massless Compton amplitudes. But this actually itself implies something that is a little more disturbing, is that geodesics are ill-defined. Okay, so massless particles traveling through gravitational fields are supposed to trace out the geodesics. But that's not how the quantum calculations behave. And it's partially because the quantum calculations give you tidal effects. Okay, they call it tidal. Okay, the tidal effects are ones that are due to finite size effects. They typically call those tidal effects. But the fact that the graviton and the massless particles can propagate long distances means that the propagation is not just sensitive to the metric at some point. Let's say there's some point here. It's not just sensitive to the metric at that point, you're sensitive to the metric at distant points also. And so you don't expect geodesics to survive, and they don't. But this is an issue then for the quantum world. These effects are small, very small, in the EFT limit. But they become of order 1 as you leave that region. So if you're in the EFT limit, you could imagine correcting for it. They become uncontrolled. Away from the limit. And so it tells you that some of the classical thought processes like Penrose diagrams and the like are not applicable for quantum effects in the deep quantum regime. Okay. The last lesson I just want to do is G and lambda. I've already done. G and lambda are not running parameters, but I always like to put it here just so we've collected it. In physical processes. So we don't have any universal definition of a running G. If you tried to do one for the potential, it wouldn't work for bending angles, etc. So there is no universal definition. Okay. And we're coming down the home stretch. The last thing I would like to talk about is the limits of the effective theory. So all effective field theories are supposed to be aware of where the limits of the theory are. And there's an obvious one, which is the high energy, high curvature. We've got amplitudes that have been growing like energy squared. So our matrix elements went like 1 over q squared, 1 plus q squared logs plus, if next order would be capital to the fourth, q to the fourth, maybe with logs, etc. There at some stage, these all they overwhelm us. And we end up with we need some UV theory. Okay. So this is an obvious limit. We expect the theory to fail, the effective field theory to fail at high energies. There are potential IR issues. Which I find actually even more interesting. The one is just our incomplete knowledge. These are perhaps technical features, but I still don't know how to deal with them. So it's interesting. And the question is whether there's any more accessible physics and more relevant, interesting physics that comes in the infrared. The basic effect is that gravitational effects build up. So even though I, right here, am in a very low curvature region, my metric function is taken to be basically flat here. If I travel astronomical distances, I can bump into a black hole. Black holes are good examples of this. Nowhere along the pathway has the curvature been big, but nevertheless, the metric builds up. My favorite example of saying this is that I can choose a metric which is locally flat and write it in terms of curvature. So these are normal coordinates. So at our point x here, so this is at some x prime minus x. This is like Taylor expanding the metric in terms of the curvatures around a given point. So even though curvatures can be small, there's some distances which are where the distance in the extreme infrared gets big enough that the corrections are of order unity. And we just don't know how to deal with this. This is a technical problem. we only know how to deal with things where the metric is small. We don't know how to deal with the large coordinates that you get in black hole horizons. Metric gets large compared to our present scale. And that's relevant because the quantum effects feel long distances. Many of the quantum effects that I gave you went like 1 over the distance cubed. And so they can actually feel things. And there are, if you try doing perturbation theory in the presence of a black hole, you actually are sensitive to the curvatures, the metric getting big there. There are other black hole questions, propagating plastic black hole. Etc. So there are potential infrared issues. They're not necessarily failures of the effective field theory, but there are limits to how much we understand. Okay, so that's perhaps been a bit briefer than I would like, but I do want to give you the sense that there are limits to an effective field theory treatment, most obviously at high energies. Okay, so I hope that I've presented the treatment of perturbative gravity with enough detail for you to see. I'm just going to close by writing a path integral where the path integral is going to involve the matter fields that we know and love. So these are path integrals. When we do effective field theory, we sometimes write a cutoff on there, which is the limit of our limit of knowledge. Which is these days around the LHC energies. And then we write the exponential of I integral d for x square root minus g times the standard model Lagrangian minus a constant plus 2 over kappa squared r plus c1 r squared c2 r mu nu. This Lagrangian describes our core theory now. All of it is a quantum field theory. G must be included in the path integral in order to get usual quantum physics, classical physics out, classical gravitational waves. We need these higher order terms here to deal with the effects, unknown effects of high energies. There can be, in addition, physics beyond the standard model, which is also parameterized by effective field theory. But the point is that GR forms a quantum field theory of the type of an effective field. And then we can pull out real predictions and real lessons from that theory. Okay, so that's where I'd like to end. There's much more to be done, of course, in quantum gravity, but this is some corner of the field where we understand some features. Okay. Thank you.
All right. Thank you, John. First
Thank
of
you,
all,
John.
really nice, serious lecture. Only the last one, but all 6 of them. Really great.
All right,
And
thank you.
also particularly appreciate the way you wound up the last lecture with this lecture. It was really nice. And yeah, you're also receiving a lot of thanks in the chat. And yeah, they really appreciate it as well.
Okay, well, thank you, and thanks for running the series, because the fact that you're preserving this and including it with other approaches to quantum gravity is a useful service to the field. So thank you for doing that.
Oh, you're welcome. But honestly, this was the first idea that came to our minds because, I guess that we all feel that enhancement and progress in all fields must be reached by constant confrontation with the different approaches. Otherwise, because when it's stuck with only one approach and only one mindset, it's difficult to move on. So everyone can learn by the others like that. So let's hope it will be like this.
Okay, very good.
Yeah. So, all right.
Okay, I am going to end the session now.
Okay, I'm sorry because there was a couple of unanswered questions.
Oh, okay, we may take a look.
But I don't know if John, if you have the time.
I have time. It's okay.
Okay, just to quickly answer a couple of them. So there are only 2 left. Let's see. The first one says, okay, what about the generations of Reisner-Nostrom metric through loop corrections mentioned in the APFL lectures?
Yes. Yeah, actually, that actually is a valid calculation, because there I'm only using classical gravity, and so that calculation actually is reliable. It's really just it doesn't depend on it doesn't suffer from Kirlian's correction because I'm doing only classical gravity there. So the calculation that's referred to is the effects of photons around charged particles and calculating the corrections to the metric, classical metric, due to photon loops.
Yeah.
And that's the classical gravity question, and the answer presented there is a classical.
So those are classical loops in some
So
sense.
but they're classical. They're quantum loops of photons. So there's no gravitons in the loop.
Okay. Thank you. Thank you for the lecture, Professor.
Yeah. Okay. Thank you.
There was one last question, which says, okay, in black hole thermodynamics, there's a procedure by which a modified statistics can encode quantum correction that can be rewritten into the metric. Is this valid?
Yeah. So I think at least perturbatively, Carolyn's objection should be considered there. So basically, the question is whether there's any either gauge or parameterization dependence of that result. So certainly in perturbation theory, Carolyn showed by direct calculation that anything you do in perturbation theory is going to suffer from this problem. And so it should be able to be addressed by looking at whether field redefinitions change that result or not, because that's the heart of his issue. I don't know in specifically that calculation how it behaves, but that's how you would answer it. You'd look to see if field redefinitions change the nature of the result.
Can I ask the last question? Sorry, it's the last one. So you mentioned in the Rice-Nostrum case, those are like classical, that's classical corrections, but are there any factors of H bar in that metric?
So, right. So again, the Reisner-Nordstrom calculation is the calculation of classical and quantum corrections around charged gravitating objects. And the calculation that we did, the one loop calculation we did, pulled out classical effects, and it also did quantum effects. So there were some terms that were proportional to H bar, and there's some terms that were not. Much like the case of the potential, you reproduce the classical pieces that are known to be there in the Reisner-Nordstrom metric, and then you found some new pieces that had a different structure that had H bars effects in them. The classical pieces actually have an interesting interpretation, and I always, when I present that, I always enjoy presenting it, because they are due to the fact that the electric fields around a charged object are not localized. So it's like tidal effects due to electric fields. The electric field goes like, the energy in it is E squared, 1/2 E squared, and there's some momentum, some T mu is not zero around this guy, a charged particle. And so the fact that has the extent is actually captured in the classical terms in the Rice-Nordstrom solution, and is found by doing Feynman diagrams when you do the Feynman diagram loop expansion. So it's a beautiful, fun little calculation to have done.
Okay, thank you, John, for the lectures, and also to the organizer for this.
Thank you.
All right.
Thank you, everybody. Then let me end the session for today. Okay. Thank you so much, John. Have a
Great,
good
thank
day.
you.
Good weekend.
Yeah, bye-bye, everybody.
Everybody have a good weekend. Bye-bye.
Bye-bye.